Okay, in this example, we're going to use a GDC in some way. I'll show you where it actually becomes a GDC, right? So this is actually, much of the problem can be done as a paper 1. But at one point, it becomes very clear that this is a paper 2 question, and I'll show you where that happens. So you wouldn't see this as a paper 1. It would become this is a paper 2. So the first few things here are pretty straightforward. If I wanted to find A, so we want to find where x intercepts. Well, that's just f of x equals 0. That implies 0 e to the minus, well, x. This is going to be times cos x, right? So if we just look at this, right? So the key here is e to the x. So if e to the x, if you had e to the x equals 0, this will always, so this is 1 over e to the x, right? So this is always going to be positive. So always positive. This becomes our main issue. So what causes cos x equal 0? Well, that happens, take a look. So if I do have the unit circle here. So you're going to want to use the unit circle for a bit, but don't memorize it. You can build it using the special triangles. If you don't know what I mean by the special triangles, you have your equilateral, right? And you have your right angle. And if you want to go over these in class, I can't, just to build the unit circle, because it's always a good exercise. It will come up over and over and time and again. This one comes up, particularly when you're starting to deal with trig. So where is cos going to be 0? Well, you know it's here. There's 0. And there's 0. So we need to look at the interval. Notice the interval that we're on. So it's going to hit pi over 2. So this is going to be pi over 2, 3 pi over 2, and again, we come back over, this would be then 5 pi over 2, right? So pi over 2, 3 pi over 2, and 5 pi over 2. So there are our points, right? So those are our x-intercepts, B. This is where it becomes, at a certain point, finding the stationary points, you're going to have to use a calculator. And that's because when we do the derivative. So it's when we do our sine diagram, you'll see where it becomes up to that point. When we do the sine diagram, at that point, you'll see where it would stop being a paper 1 and becomes a paper 2. Hence, the whole thing is a paper 2, actually. So let's just do the derivative. So if our original function is e to the minus x cos x, right? So I'm going to take the derivative of this. This is just e to the x times minus 1 cos x minus, well, I'll do plus e to the minus x minus sine x. This then is minus e to the x minus x here, cos x minus e to the minus x sine x minus e to the x. I'm going to minus x, pull out the e minus e to the minus x, cos x plus sine x. Okay. Again, we already know when we want to find our critical values. So find critical values. So we want to find right? And that is one of the cases is going to be x equals 0. So we're going to set that because that's where our mins and maxes. We already found our zeros, so we know where they are. Now we want to find the mins and maxes. Okay, well, here we go. Let's just go for the hunt. So we're going to see right here. We already know if for this term, we already know that e to the minus x, if that's equal to 0, then you know what? It's already always going to be 0. So, or no, not always 0. It's always going to be positive. So we don't care much for that one. Where is it really coming from? Well, it's the case where you have sine or cos x plus sine x is equal to 0. This is the one that's going to produce actually our whatchamacallit, max and mins. So watch what we're going to do here. So there's a little bit of ingenuity here. So why don't I do it a certain way? Why do I do it a certain way as opposed to another? Well, because I'm creating a tan in the end. So what I could do is I just did it this way. And I know, well, notice what we have. Cos x, sine x. It already looks, this is, you'll see what we're going to come up with. And this will be, I'm going to say cos, oops, I'm going to say this. Oh, yeah, sine x is equal to minus cos x. If I then divide everything by cos x, so I'm going to have sine x divided by cos x is equal to minus 1. So notice if I did here, just as a play, just see for yourself what happens if you did this. If you asked yourself this question, why did I do it this way, right? Why did I do that as opposed to this? Why didn't I say cos x equals minus sine x, right? Why didn't I do that? Well, you could do that, right? But you'll see, notice it's a minus 1. I just have to do an extra step of multiplying through both sides by -1, and we still arrive at this. So dot, 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 you get to a certain point, you still have like a negative tan x is equal to 1. Well, negative tan x doesn't help us. So we would multiply both sides by -1, and you get your -1, because we know that this ultimately, right, I'm just make it thick right here. This is sine over cos. Well, that is tan x. So we know tan x equal -1. So what do we have? So we're going to then have -1. Where is tan -1 on our unit circle? So let's just see tan -1. Notice right here, this is any time when you have the same value over the same value, like a over a is going to give you a 1. So you know it's this one, this one, this one, and this one. Now you just have to figure out which ones are positive and which ones are negative. This one is going to be positive, +1, +1. I don't care for either one of those because that's our tangent. Tangent here is 1. Tangent here is 1. I'm not looking for 1. I'm looking for -1. These are my negatives. So what are my values there? Let's take a look at the value. 7 pi over 4 and 3 pi over 4. Now, this is the thing. When you're thinking about this, you're not going to have the unit circle. This is why knowing your special triangles becomes very important, right? And where they fit, and where tangent is going to be positive and negative. And this is where a very important property called, I think it's this way, cast. You remember? Cosine here is positive. All are positive. Sine is positive. Tangent is positive. Now that's easy. If tangent here is positive, then, and notice that each one of these are going to be positive, this tangent is also going to be positive. So you automatically know it's quadrant. So this is, where do I put it? This is quadrant, I think, how do we count this? This is quadrant 1, quadrant 2. This is quadrant 3 and quadrant 4. Sorry, I forgot how to do quadrants. But there it is. I kind of remembered last minute. There you go, right? These are your quadrants. So you're going to want to remember these little things. And you can remember it by cast, right? CA, and you're always starting in the lower left corner in quadrant 4, and you move around. And then you start in the upper, for the quadrants, you start always in the upper right, right? And then move along. So we can now, with that information, we can actually now use our Sine diagram, right? So we already know the points where you're going to have the min or max. So this is going to be 3 pi over 4, was it? Yeah, 3 pi over 4. And this is going to be 7 pi over 4. This is going to be your min and max. Now, right here, okay, this is where it gets tricky. This is where it turns into actually the benefit of being a GDC. Because this is where approximately this is equal to, and once you start using numerical values like this, it becomes helpful, right? So this is where a GDC is what you're going to want, right? So this is only, at this point, it stops being a paper 1 and actually becomes a GDC. That means it's paper 2. Because the calculations for this become incredibly laborious and difficult having to do it by hand. So avoid that because this is not going to be a paper 1. It is a paper 2. Because you're going to have to then plug in, let's say this value, 2.34. Here, let's say we're going to put in something lower than that. So this could be 5.4. And on this side, you could say 5.6. And you would put this into your f prime of x. So each of one of these, this one, and this one, you're putting right in there, right? Those are your x values you're putting in. And when you do that, what you see is this becomes negative, this is positive, and this is negative, right? So when you test it, go by all means, do it, and you'll see. This then becomes a happy face. This one is sad face. So you know that this is your min and this is your max, right? So there you go. We already found it just using first derivative test. So right here, what this is not showing you right here is this. So if I blew this up, you would actually see the following. It would go so you see right here should be, this is your minimum, right? There's a minimum right here. This is your, I think it's what, 3 pi over 4. But there is a maximum right here. So it's going to pass, one of your zeros is going to be, I think it's 1 0. How many zeros we have? Yeah, there's your pi. So this is right here is your pi over 2. But you know there's two other zeros, and that's one of them is here, is 3 pi over 2, right? 3 pi over 2 is going to be over here. And then there's going to be another one, 5 pi over 2. So the line's coming, actually, you don't see it in here, right? So this is a scaled up version. So you'd actually have to blow this up to see it. So it'd come up, over, and back down. Whoops, I missed that spot. So it should come up, over, and back down. And the peak right here, this peak, so our max this is our 7 pi over, what was it, 4. Perfect. And it fits right into the middle of them. So you just don't get to see this peak in here. It is there. Believe me. Zoom in on it on your GDC, plug it in, zoom in on it, and you will see. It's guaranteed that it will be there. right? So you just don't get to see it due to the scaling of this. You'd have to figure out what kind of scaling would work to be able to see that, right? So I actually would encourage you to do that.